Resistors in series and parallel. This is probably one of the more challenging aspects of this chapter, and really where most of our problems come from in terms of the homework problems that are assigned and test problems that are assigned. In many of these problems, in many of these examples, what we do is we take a more complex system, where resistors are in parallel or resistors are in series, and reduce it to a simpler equivalent system. So we're going to go through a step-by-step process of how we go from a more complex circuit to a simpler circuit, and then in the end we'll go from our simple circuit and work backwards using Ohm's law, V equals IR, and I is equal to V over R, to find out how much current is going through each resistor and what the voltage across each resistor is. So resistors in series, this is the easier part. When we have anything in series, everything within this series, one after the other, has the same current. You might have different potentials across them, but they're going to have the same current. We can use this idea that they have the same current to find an equivalent resistor to two or more resistors in series. So again, let's take a look at this example right here. We have our battery. It's hooked in series to two light bulbs. Each light bulb has its own individual resistance. Okay? So whatever the potential difference is of this battery, there'll be a potential difference drop across the first light, then a potential difference drop across the second light, and these two voltage drops will be equal to the EMF of the battery. Okay, so again, here's our circuit diagram of the system. We have our EMF, we have our source of voltage, whatever this is. If it's 12 volts, then I can imagine we might have 6 volt drop across here, 6 volt drops across here, and then the current returns to the battery right there. Now, once again, the potential difference drop is going to be the voltage drop across the first plus a voltage drop across the second. By Ohm's law, V equals IR, that means the potential difference drop across the first bulb is IR1. The potential difference drop across the second one is IR2. So now our equation becomes this. Our potential difference is equal to I times the sum of the two resistors. This means that I could replace these two light bulbs with a resistor that was R1 plus R2 and draw the same exact current, have the same exact potential and current. Okay? So really, looking at the above system, the equivalent resistance of two resistors in series is just the sum of the two resistors. Okay? So the first resistor was, let's say, 10 ohms, the second one was 20 ohms, 10 plus 20 is 30. It would have the exact same effect if I had just one resistor there at 30 ohms. The reason why we do this is because it's much easier to solve for a single resistor than it is for two resistors, okay, or two or more resistors. So again, when we're analyzing these circuits and we're taking resistors in series, as long as they're all in series, they're perfectly in series, we can replace two or more resistors and replace it with an equivalent resistor equal to the sum of all the resistors in series. It's very important to note that if you have resistors in series and parallel, you've got to just group the ones that are in series by themselves first, and the ones in parallel by themselves, until you get something that's purely in series or purely in parallel. Here's a good example of resistors in series. Most Christmas lights are now LED lights. The old incandescent bulbs, however, were all in series. So if the filament would kick out on one of these bulbs, if it would break, you would then have a problem where the current could no longer flow, because the current that goes through the first one goes through the second one, all the way to the 100th bulb. Now, to fix this problem, they actually created these jumpers where the open circuit here would create a high resistance and force the current through this jumper, which would then fuse to the two electrodes right here. or the two conductors that were originally attached to the tungsten, that would short circuit this and allow the current to proceed even though that particular light bulb was no longer working. Let's do an example of 4 resistors in series and see how these 4 resistors become an equivalent resistor and what the voltage drop is across each, what the current is through each. Okay, so we have here a 2 ohm, a 4 ohm, a 5 ohm, and a 7 ohm resistor. We want to first of all find the equivalent resistance of this circuit. How do we do that? Very simple. The equivalent resistance of all 4 of these is simply equal to the sum of all of them. 2 plus 4 plus 5 plus 7. Okay? That's easy. B, find the current in the circuit if the EMF of the battery were 6 volts. Well, if I know the equivalent resistance of this whole thing, and I know the EMF, 6 volts, I equals V over R. I take the voltage divided by the equivalent resistance, and I have the current. Remember, if we follow the current, it's going to go through each individual resistor before it returns to the battery. So the current through 1 is the current through 2, is the current through 3, is the current through 4. Let's look at this mathematically. Again, finding out the equivalent resistance, that's easy. 2 plus 4 plus 5 plus 7. That's 18. So the total effect of these 4 resistors in series is the same as an 18 ohm resistor. Okay? Now we have the 18 ohms. Once again, I want to find out how much current is going through here. V equals IR. I equals V over R. 16 divided by 18 gives me 1/3. So I get 1/3 of an amp traveling through this whole thing. Okay? So very straightforward for series circuits. Whatever your current is, it's going to be the same through everything. That current is going to be the same. Series, we have the same current. Parallel, we have the same voltage. We'll get to that next. Now, we want to find the potential difference across each resistor. Yeah, I know the potential from the battery. I know the current that goes through each one of them, 1/3 of an amp. I can now use V equals IR to find out each potential difference drop. Okay, the first resistor is only 2 ohms. So 1/3 of an amp at 2 ohms is going to give me 2/3 of an amp through there, or 0.67 amps. The next resistor has twice as much resistance. So I get twice as much voltage drop across that one. Okay, same current, twice the resistance, 1.33 volts. The 5 ohm resistor, 5 times 1/3 is 5/3, or 1.67. Finally, with the 7 ohm, 2 1/3. So, let's add these all up. 2/3 plus 1 1/3 plus 1 2/3 plus 2 1/3. So I have 2/3, 1/3, 2/3, 1/3. Okay? So basically 6/3, that's going to give me 2 volts. I'll carry the 2 over here. 2 plus 3 plus 4, 2, 3, 4, 5, 6. 6 volts is my total. Okay? So some very important things again. The current is the same through all of them. All right? For series, the current is the same through all. But the voltage drop is going to be equal to the sum of the EMF that's applied here. So if I have 6 volts here, this voltage plus this voltage plus this voltage plus this voltage, they're all going to add up to equal a total equal to the EMF. All right, resistors in parallel. Here, we switch the game around. In series, the current is all the same. In parallel, they're hooked up, so the potential is all the same. The voltage is all the same. Okay? The current, however, is going to branch out. Now, look at this setup right here. Here, I have this resistor, which is basically a light bulb, in parallel with this resistor. If this is a 12-volt battery, this lamp gets 12 volts, and this lamp gets 12 volts. The current, however, is divided up. Some of the current will go through this light right here. Some of the current will go through this light. Okay, it has 2 paths it can go by because this is a parallel system. So this current plus this current will equal the total current that I get from the battery. So equivalent resistors in parallel. If they're in parallel, we say the equivalent resistor is equal to, I should say the reciprocal of the equivalent resistance is equal to the sum of the reciprocals. Now, why is this so? Well, going back to this case right here, remember, we're breaking up the current. Current is equal to voltage divided by resistance. Okay? So if we imagine that the total current is equal to I1 plus I2 plus I3, if the voltage is all the same, I is V over R. The voltage divided by the equivalent resistance is equal to V divided by R1, V divided by R2, V divided by R3, so on and so forth. I divide both sides of the equation by V, I get this equation here. Okay? So again, the equivalent resistance for parallel, we take the reciprocal of the equivalent and set that equal to the sum of the reciprocals. Oops. Let's consider three resistors in parallel. If this is 18 volts, they're all in parallel, so everybody's getting 18 volts. All right? The current that comes from the battery will branch off to become I1, I2, and I3. We're going to calculate the current through each resistor. We're going to calculate the power delivered to each resistor, okay, and to determine the total power. We'll find the equivalent resistance, and we'll find the total power based on the equivalent resistance. So again, what do we have? 18 volts across every resistor. I want to find out what the current is. Okay? The current is equal to voltage divided by resistance. That's V equals IR, solving for I. I is V divided by R. For the first resistor, under 18 volts, it has a resistance of 3 ohms. It is going to allow 6 amps of current to flow through it. It is by far the least resistive element here, so the most current is going to go through it. I2, 18 volts, with a resistance twice as much. Twice as much resistance, half as much current through it. Okay, so I2 has 3 amps going through it. The last one has 3 times more resistance than this, so it'll have 1/3 the amount of current. 18 divided by 9 is 2 amps. And we see here 6 plus 3 plus 2, 11 amps of current are going to flow through this whole thing, with 6 going here, 3 going here, 2 going here. Alright, so we did part A. We found the current through each individual resistor. Part B, we can also calculate the power that each dissipates. Remember, the electrical energy that's coming from the CMF source is going to be dissipated if these are resistors as heat. If these are LEDs, they'll be dissipated as light and heat. So, power is equal to current times voltage. Here's the current through each of them. Every one in parallel is under the same voltage. The first resistor, 110 watts. Second resistor, half the amount of current, half the power, 54 watts. Final power, hopefully I said watts up here. I have current times voltage, only 2 amps, 18 volts, 36 watts. What is interesting here is in parallel, it's actually the lower resistor that uses up the most power. Okay? A little counterintuitive. We think that if it's more resistive, it would end up using up more power. But it's actually, power dissipated really goes by the square of the current. So it's important to understand that if we got a lot of current going through something, we're typically going to have a large amount of power dissipated. So 110 plus 54 plus 36, the whole power dissipated by the system, 200 watts. Okay? Let's look at C. Find the equivalent resistance. 1 over R EQ is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So we have 1/3 plus 1/6 plus 1/9. The least common denominator there is 18 ohms. So 6 over 18, 3 over 18, 2 over 18, I add them all together. 6, 3, 2, we get 11. 11 over 18, but this is the reciprocal, so we've got to flip it. 18 divided by 11 is 1.6 ohms. So this whole system here acts as though it only has a resistance of 1.6 ohms. Okay? Notice that when we put these in parallel, the equivalent resistance is much less than each individual resistor. Okay? My lowest resistance here is 3 ohms. My equivalent resistance is 1.6 ohms. Why? Because we're giving the electricity more than one path to go through. So we've lowered the resistance. It's almost acting like we're adding other pipes to this whole system to allow more electrical flow. Last one, find the total power delivered for the equivalent resistor. Again, our equivalent resistance was 1.6 ohms. I'll put that into my power equation. Power is equal to current times voltage. I could have used the current that I found originally, or I can just use the 18 volts, divide that by the equivalent resistance, and you get 200 watts. Okay, so if I've used an equivalent resistor here to calculate the power, I get 200 watts. If I use the power dissipated by each individual one, I get the same answer. Okay, so the equivalent resistor, it really is fine for finding out any of the different elements of a circuit. Again, we always want to simplify the circuit. This is a little more complicated than what we had before. You want to go from everything that's in series and everything that's in parallel, combine them first to get something that's in pure series or pure parallel. We want to find the equivalent resistance, and then we want to find the current based on the equivalent resistance if this were hooked up to a 42 volt battery. So a little more complex than what we had before. 2 resistors in series, 2 resistors in parallel. To simplify this system, I can approach this one of 2 ways. I can make this parallel set right here into 1 resistor. That'll give me 3 in series, and then reduce the 3 to 1. In this case, I'm going to reduce the 2 series into 1 and reduce the parallel to 1, and then combine those 2. Either approach is fine, whatever approach you want to use. But again, it's important to identify what is purely in series and what is purely in parallel. This 8 and 4 ohm resistor is connected to the 6 and 3, but they're not connected in series. So we combine the resistors in series and parallel. 8 plus 4, remember, for series resistors, we add the resistance together. 8 plus 4 is 12. In parallel, we have 6 and 3, so 1 6 plus 1/3. 1 6 plus 2 6 is equal to 1/2 or 1/2. We take the reciprocal 1/2, we get 2. Okay, I didn't do that math on the board, but you can do that on a piece of paper. You're going to get the same result. Now we have the 2 and the 12 and the 2 in series with one another. 12 plus 2 is 14. Here's the equivalent resistance, 14 ohms. So these 4 resistors act like a single 14 ohm resistor. Okay? And the current goes through the first 2, branches off to go through these 2 before going to the other side. Okay. And again, here's the actual math. 8 plus 4 is 12. That's this branch right here. There's a 12. Again, this other one, we take 1 over the equivalent resistance is equal to 1 over R1. 1 over R1 plus 1 over R2. If we solve for just the equivalent resistance, it looks like this. Okay. Again, 1 6 plus 1/3 is equal to 1/2. To the reciprocal of 1/2, and we get 2. Now we're down to 12 and 2. We add those together. 12 plus 2, they're in series. Even though this is an equivalent resistor, it acts like a real resistor. 12 plus 2 is 14. So our equivalent of the entire circuit is 14. Ohm's law of equals IR. We want to find out how much current goes through there. I equals V divided by R at 42 volts. Resistance at 14 ohms. we get 3 amps of current. Okay? So 3 amps of current are going to go through here. Tracing back, 3 amps go through here, 3 amps go through here. Okay? Then it's going to branch off going through here and here. We could use that to then calculate what the potential difference is, all right, through this. But actually, this is 3 ohms, this is 6 ohms. I know I'll get 2 amps going through this bottom one, 1 amp going through here, just because this is twice the amount of resistance as the one down there. Okay, so 3 amps, 1 amp is going to go through here, 2 amps is going to go through there. Remember, this equivalent is 2 ohms. If we calculate the potential difference across this, given a current of 3 amps, okay, 3 amps divided by 2 ohms, 3 divided by 2 is 1.5. If I multiply 1.5 times 6 right there, that is going to give me a 1.5 times 6, 9 volt potential drop across this one. Okay? And then you can use that to find the current. Again, 6 volts. Again, I1 is going to be 1 amp. I2 is going to be 2 amps. Again, here is the potential difference divided by the resistance. Let me just go back for, again, 3 times 2 gives me my potential difference. Okay? So, in summation, when we have resistors in series, we take the sum of each individual resistor. If we have them in parallel, we take 1 over the equivalent to be equal to the sum of the reciprocals. Last example. Okay? We are going to skip some of this. Take a resistor set and look at these series in parallel. One more thing here. We'll take a look at this one right here before we get to that, because the last problem is really the most important to look at, even though it only has 3 resistors. Doesn't matter how complex these sets become. Just do this by step-by-step process. Take anything in series, reduce them to an individual resistor. Anything in parallel, turn that into an individual resistor. These 2 then become in parallel. You reduce that to 2 in series. Same thing here, 2 in series. Then the series becomes an individual, and then you get 2 in parallel here. So again, step by step, break your complex circuit into as simple of a circuit as possible. Once you're there, if you need to go back and find the current and resistance through individual resistors, you can do so using Ohm's law. Okay? I promised to show you this one. This is a real good step-by-step process for showing how this is done. I would reduce it to the simplest form and then go backward to find out what the voltage across each resistor is and what the current through each one is. Okay, so let's start over here. We have a 4 ohm resistor, a 6 ohm resistor, and a 3 ohm resistor. These 2 are in parallel, so I'm going to simplify them first. 6 and 3, remember 1 over the equivalent is equal to the sum of the reciprocals, 1/6 plus 1/3. We saw earlier is equal to 1/2. We take the reciprocal of that. Reciprocal of 1/2 is 2. And now we have 2 resistors in series. In series, we add them. 4 plus 2. 4 plus 2 is 6. We have the simplest system right here. Again, this wasn't really that complicated, but I want to show you a simple system to help you realize how to do this. I have my equivalent resistor. Now I want to find out, what is the total current that flows through the system? Okay? 6 ohms, 18 volts, V equals IR. So if we want current is equal to voltage divided by resistance. 18 volts divided by 6 ohms, 18 divided by 6 is 3, so 3 amps is going to flow through this whole thing. So looking at right here, I'm going to have 3 amps coming through this first resistor, some of it going through here, some of it going through here, and then back. The whole current drawn from the battery is 3 amps. Let me step backward. Let me go to this case here, write a 2 ohm and a 4 ohm resistor, total of 6, in series with one another. If this is 18 volts, I want to know what the voltage is across each resistor, or equivalent resistor. Okay? I found out that I have 3 amps flowing through the whole thing. So for my equivalent diagram, I'll have 3 amps going through here, and 3 amps through this equivalent resistor. Okay? 3 amps, 3 amps. Well, V equals IR. The voltage across here, the potential difference across here, is the current through it, 3, times the resistance, R, 4. 3 times 4 is 12, so I get 12 volts here. Same thing for here. Voltage is equal to current times resistance. I have 3 amps, there's my I, my R is 2, 3 times 2 is 6. 12 volts here, 6 volts here, that agrees with what I have up here. 12 plus 6 has to be equal to the total voltage that I have here. Okay? Finally, I work backwards. Across this 2 ohm resistor, I have really 2 resistors in parallel. 6 ohms and 3 ohms. Okay? I already know that the voltage here is 6 volts. Right? So I can use I is equal to V divided by R. 6 volts divided by 6 ohms, 1 amp goes through here. 6 volts divided by 3 ohms, 2 amps are going through here. So 2 plus 1 is going to be equal to 3. My dogs agree. So here we're able to take the circuit, reduce it to an equivalent resistor, all right, work backwards and find the current through each resistor and also the voltage.